Hello everybody, my name is Drew Bailey and today we're going to be talking about Faraday's Law in Lab 5. So let's talk about what we're doing in this lab. On the left, there's a diagram showing the setup. The top cylinder represents our bar magnet, with the north side facing down or towards a non-ferrous tube. In this case, a tube of aluminum foil was used. The tube must be non-ferrous because a ferrous tube will attract the magnet and make the experiment useless. We will observe how long it takes the magnet to fall through the tube. We notice that the magnet falls through the aluminum tube slower than it falls through air. To explain this phenomenon, we will talk about some of the fundamental physics concepts it used. The main principle acting in this lab is Faraday's law and Lenz's law. Faraday's law tells us that a changing magnetic field leads to a flow of electric charges or current, and Lenz's law dictates the direction that current, and thereby the force, will oppose the magnet as it falls. We can use the Biot-Savart law to determine the magnetic field on the tube. By Newton's second law, force equals mass times acceleration. We can find out how much force will be acting on the magnet due to gravity. Using the sum of these forces, we can see that, while the force of gravity is still larger, making the magnet fall, the contribution to its force by the tube will slow down its descent. According to our time trials, the time the magnet took to fall through the tube was approximately 1.18 seconds. In comparison, the computer simulation modeling an ideal world tracked that the magnet would fall in about 0.535 seconds. Let's now take a look at our aluminum tube. For this assessment, I used a tube of aluminum foil 28.8 centimeters or 0.228 meters in length and a 0.5 centimeter or 0.005 meter diameter tube. We use a non-ferrous tube for the experiment to prevent the magnet from sticking to the sides of the tube. This would happen in a ferrous tube. To begin our experiment, I took videos of the magnet falling through the tube and re-watched them in slow motion to find out the average time that it took for the magnet to fall through the tube. As we see here, the magnet took an average of 1.18 seconds to fall through our aluminum tube. This can be compared to the time it would take the magnet to fall through the same distance without the tube. In free fall, the magnet takes 0.242 seconds. The next part of our experiment is simulating the magnet falling through the tube. To do this, we use an iterative function that uses the equation for flux and the properties of the bar magnet to estimate the time it took. Here we see the computer code used to calculate the derivative of the flux in this experiment. This was then used to find the current in each ring or section of the tube using Faraday's law. After this, the properties of the magnet were used to find the force of the magnet on the tube. This results in the model shown here. The tube is shown in gray. The motion of the magnet is shown in two rings, a red one and a blue one, which represent the directions of the current in the tube above and below the magnet. This computer model also returns a graph of the process. Here we see the speed of the magnet over time. The drop in the beginning shows the magnet being affected by the current generated, and the lower, constant velocity shows the magnet's slower descent through the tube. In conclusion, did the non-ferrous tube make a difference in the speed at which the magnet fell? Did our results make sense? Yes, they do. As shown here in both the computer simulation and the experimental results, they show the magnet will take longer to fall through the tube than it does during free fall. Does this make sense, though, that the magnet takes longer to fall in the experiment than it does in the computer simulation? Our computer model does not take into account friction of the magnet in the tube or human error in performing the experiment and reading the results. Another question we ask ourselves is, how would cutting holes in the tube affect the outcome of our experiment? Because the amount of non-ferrous material would be lower, the resistance would be lower, and therefore the current would be lower and the magnet would fall faster. We can also imagine a scenario in which the tube's resistivity is equal to 0, in which case our formula V equals IR and our knowledge about physics theory tell us that the current would stop and the magnet would not move at all.